Actually, out of curiosity, just a quick show of hands here. Who has an interest in games, and that's the reason you're here? Just yeah, I kind of guessed as much. Emulation is that kind of topic. And it's probably just as well because this is kind of about a half-hour talk, so I'm going to actually start this off with a bit of an odd one. I'm actually going to recommend you watch sort of 2 other videos, well, more precisely one long video and 3 of the very short ones, so about 10 minutes each. And the reason I'm going to recommend that to you is because, frankly, as I said, we have about half an hour here. We're not going to be able to go into huge depth as to how everything works. This is more of a case of if you want to pursue this topic, you'll go look at the documents, you'll do some code, you'll inevitably discover that you've made some immense fault in understanding the architecture and operations and stuff. Hopefully you'll come to this talk, understand various goals along the way towards getting you to a basic, playing a basic game, and then you'll go back and work on this again. Because when I started off this, down this path, emulating Game Boy, it must be on and off about a year ago now. There were no courses, and there still are no courses sort of teaching you how to build an emulator, right? An emulator being a virtual recreation software of some piece of hardware. In this case, a Nintendo Game Boy console. But there were no, courses about it. There was no real in-depth testing. There was no sort of talk about that. If you look up on YouTube, for example, you'll see there's a few videos where someone has attempted to perhaps start a Game Boy in various languages, including Python. But I've yet to actually see one where they've gotten to actually being able to run a game as such. I think the furthest I've seen is a 16-part video series in Rust where they finally get to the initial boot logo scrolling correctly down the screen. So needless to say, there's quite a bit of room for potentially going wrong, especially if you don't know where you're going along the way. And that's the main topic of today, I think. So just by the way, sorry to go into these. So the top one there is called the Ultimate Game Boy Talk. And it very much is from a technical perspective. This will give you all the understanding of how every single component works, underlying architecture stuff. I do recommend at some point, by the way, that you do at least read up a bit on, how something like a CPU works, for example. Because you are going to need, there's no real nice way to put this. You can do a bit of coding and come back later on if you want to, when you have a better understanding. But to carry out certain operations, you will need to know how some of this actually works. I certainly jumped in head first, not knowing a huge amount, or thinking I knew more than I did, and it ended up burning me several times, you'll see along the way. And the 3 short videos at the bottom are kind of in the same vein, but they're more specifically targeted to certain individual items. Okay, so... Well, first of all, I suppose it asks is, well, why would you recreate a Game Boy, And there's a couple of different reasons for it. I mean, one is obviously the games. Obviously, most of you are here for that. I presume at least a fair amount of you have played Game Boy games. They might be quite simple, but they can have quite a depth to them. But there's over 1,000 titles for the basic Game Boy alone. So you have quite a bit of wiggle room there to, implement stuff that you want. I presume most people here probably played or at least heard of Pokemon. That's a very popular one. And Mario and some other ones as well also have their start in this. But it's quite a simple device architecturally compared to a lot of modern machines. There's no operating system, for example, beyond that initial scrolling Nintendo logo that when you start on the console. And that's literally 30 individual bytes, and everything else after that is completely dependent upon what's in the cartridge. There's no operating system full stop. And that you probably won't initially understand what's the importance of that. Well, to give you one example, there's no way to actually get a truly random number using a Game Boy in any shape or form. Instead, what they do is a quick hack where they try to get the memory location where a certain item is stored, multiply it perhaps by the number of steps you've taken in the game, perhaps, or the number of CPU cycles there have been executing instructions, and then maybe add something else, and that ends up being the random number. And if you've ever been interested in game speedrunning, you might see this is actually sometimes how they get certain, say, Pokemon spawner for certain enemies to appear in certain positions, because they literally can be manipulated in that way if you're precise enough. Excuse me. But also that, frankly, if you're looking for a good challenge, this is actually a very good console to approach, because while it's relatively simple to understand, there's quite a lot of potential hidden depth to it. It's not tremendously difficult to get to the stage where it'll play Tetris, which is kind of a very basic game that involves implementing a few things, but you don't have to go absolutely mad with it. But if you want to go all the way with the Game Boy, down to the very millisecond, it can take you quite a long time. And just to give you a heads up in advance, there have been quite literally transistor-level recreations of this thing that are also not perfect. So don't be too hard on yourselves if you have troubles along the way. And also, as I sort of began at the beginning, this is a very well documented system. It's been around since 1989. It finished production in 2000, and it's very much one of the most popular scenes for individual developers to make their own, what we call homebrew games, their own games themselves. There's a lot of good series that have their starts on there or have their best games sometimes on the system. It's very well documented how it works on a hardware level and all sorts of little odds and ends, but there's not necessarily a direction to how you can sort of start this and get going and keep momentum and what are some good checkpoints along the way towards actually getting a game running. In fact, you'll see at the bottom here, I've labeled something called the Pandoc. So this is sort of the main reference guide you'll keep coming back to when you're implementing stuff or you're looking up how certain things work. And this is about 270 pages long. And it's quite detailed, and it's not even, it links to other documents frequently as well. So you've got quite a lot of material to go through here if you want to, potentially go all the way down the rabbit hole and implement absolutely everything. But thankfully that's not really necessary, as we'll see. So a Game Boy consists of a lot of different components, but this is kind of some of the stuff you will have to recreate. So the CPU, probably a given. It's the bit that handles all the instructions and tells things what to do. Memory, so there's different forms of memory. So there's video memory, which we call VRAM, RAM, which I presume you know what that is. There's also audio memory, and of course the cartridges themselves which carry the games can actually have extra memory built on board, which we'll come to in a minute how you handle that. The graphics, so you might have heard of a GPU, graphics processing unit. This is actually called a PPU, a pixel processing unit. And so how that ends up working. There's also the audio part, which I have to confess, full disclosure, I've not got fully working yet, which is why you're not seeing it here with the wonderful introduction of a scrolling logo saying PyCon Ireland. I will hopefully fully release the thing when I have that working. The input and output, so how you get user data, user input, so how do they know you've pressed the jump button, for example, and there's kind of a lot of other items. You get an idea, I think, there on the side on how much there is to actually recreate. This is a high-level architecture view. So where do we start? Well, we start with cartridges, or more precisely, how we actually get the game data and structure it in some sort of way. So there's a lot of potential stuff we can get from the cartridge, not just the game data itself, but there's also sometimes extra memory that's been allocated. The way that some games are actually saved, sometimes you can't save games and you just play only, but sometimes you do, or you are able to save them, and they literally have a small bank of RAM with a battery supporting it, and that's how literally you save, is just doing a dump of whatever's in memory into there. Sometimes they have extra peripherals as well. Now, for the most part, you won't really care about this because to get Tetris running, we don't actually have to care too much about them, but we need to format them in a certain way that we can access this information later on. And for testing, we're going to kind of come up these again as we go through, but there are two main sort of test cases that you can use to start out with that are a bit more gentle than trying to run with just a pure game. So the first one's called the DMG Acid 2. So this is a community-based ROM, or read-only memory file, that creates a sort of smiley face you can see in the bottom right there saying hello world. And this is a kind of simple enough, but it uses just a little bit of everything that you would need to get a game running to actually create it. So it's very much worth using this as a reference point when it goes along. It's not a very big file either, which helps. Excuse me. And the other one, which I haven't pictured here because Nintendo is very keen sometimes on copyright striking this when it appears, is the scrolling Nintendo logo. So when you boot up a legitimate copy of a game, the Nintendo logo will appear at the top of the screen and go down slowly to the center, a little bing will play, and then you'll go to the game itself. This is the first item located at the head of each individual cartridge that was officially manufactured by Nintendo. And it's literally the only copyright system the game system actually has. You literally just perform, you read the actual bytes that you're given, and at the very end it performs a sort of equals comparison to say, are the bytes that it's been given equal to what it expected? Because of course you can't really copyright code, but you can trademark a logo, so that's literally the only copyright that there was for over 10 years for this system. So I won't show it there, but you can literally find these, by the way, by literally Googling them. I have included a link to the GitHub repo there for the DMG Acid 2 one. And boot ROM, you can Google it, and it's available on Wikipedia. Oh, not Wikipedia, a wiki for the Game Boy. So how do we actually start with this? Well, my naive approach to begin with was simply reading in with read lines. I'm sure you're all familiar with that operator in Python. You get, the files you're given, by the way, are .gb files. They're literally just binary files that are, we call sort of GB files because there's a certain header section inside them that we care about when we finally parse them, but don't actually make any difference to how it's going to be read in. I mean, you can get these files, by the way. You can get a little item called a consolizer that will take the files from the Game Boy games themselves. It plugs into your computer. It's about €50. Not fantastic, but it's the good way to actually get these games legally. I obviously can't condone piracy. No, I actually own all the games I've tested on. I will be saying that. So, as I said, my raw initial approach was to simply take this binary file, a .gb file, read it into a big array, a very big array, and then try to operate directly on that. Now this, to put it mildly, did not go very well. I think I had 4 separate files at the time, and I was constantly having to essentially reread the entire file to get just one specific piece of information, which was an utter waste of time. You don't need to do this. So the problem is as well is that a certain section of the file, not just for the Nintendo logo, but for other metadata you will need as well, is actually at the very beginning. And these are actually quite useful items to sort of section off, because you can directly index into them using hexadecimal, which you'll see now in a minute. So these get resolved by Python as numbers, and it's like if you're directly indexing into a position in a list. And thankfully these items are actually hard-coded to begin with. So for example, there'll be the license code if whoever produced the game, and then in terms of more useful data, there will be stuff like, does this cartridge actually have extra RAM on it, for example, for saving? Does it support read-only memory? How much memory is there in general? So how much memory will it need to locate? The title of the cartridge and stuff like that. And we need to get all this data at the very beginning, because while we don't necessarily care about, say, the licensing, it doesn't affect how the game is played. There are, as I said, sort of we need to know if there's extra memory on board. We need to know if there's actually an ability to save the game. And sometimes while we do read mostly from the cartridge, there are some games that support actually writing to the cartridge itself as well. Sometimes for saves and sometimes for other items. And we use these, we sort of control this memory using something called a memory bank controller. So it's not going to play a big part today, because you can do a lot without actually needing to implement this. But it is worth keeping in mind for the future. So your design should be, from the very beginning, very flexible to be able to take into account that maybe you'll need extra memory to be allocated when you're creating, reading into memory what your file is. Because the Game Boy itself only has about 16 kilobytes of RAM, so you're not going to be, the biggest cartridge size that you can get, I think is about 2 megabytes, which sounds absolutely tiny to our ears, but you're not going to be able to load that into memory. Or the memory of the Game Boy, I should say. Now, for basic games, it doesn't really matter, but, you know, if you want to play something like Pokemon, for example, it will do, unfortunately. So the best approach for this I found was in a very test-driven manner. So using not just the 2 test ROMs that I told you earlier on, but also there are others available to the community as well, which I'll link to. And it's worth doing a few of these, simply because, as I said, at the very beginning, indexing directly in to get this data is actually quite useful, and setting it in a certain manner is a good way of confirming that you've actually read and set everything in the correct places for what it should be doing. So let me just give you an example here. So this is how we index and get the cartridge type and the cartridge size in the middle here in Python. So we've literally just read this into an array, and we just simply select the individual place. So if you can, it would help if you think of the hexadecimal value there for cartridge type at the very end, so 0147. Python will automatically resolve this to a number that it will then directly go into that index position in the array you created. So in this case, it retrieves our cartridge type, our ROM size. There are other items as well. The cartridges also, rather just to note, have a thing called a checksum at the end. So you might be familiar with this from networking. And this is something built into the cartridge, which I think is literally a few individual bytes, where it does a for loop and essentially compares them. And at the very end, it compares it to a given number and expects that to be equally matching. And if not, it's not considered to be a valid cartridge. You're given the logic for this, by the way, when you look up anything about cartridges whatsoever. So don't worry about implementing that. But it is worth noting, and this is the format I sort of chose on the bottom right there to represent in a test whether something got loaded successfully. So this is actually for the DMG ACID 2. So we've got the title, we've got the cartridge type, we have the ROM size in raw bytes. Please ignore the spelling mistake at the end there. I didn't notice that until now. It's not bytes 2. Is there extra RAM on board? No, it'd be 0. And has the checksum passed or failed? So if it's failed, then it's not a valid file. So that should be kind of straightforward enough. So as I said, DMG ACID 2 is kind of very good for this. The Nintendo boot logo doesn't really have necessarily anything fancy to it. It usually runs before this section actually does as well, but it's also worth passing through. It's just to make sure you can actually directly index into whatever you need. It's the most basic form, making sure you've got this data in the correct format, because if you don't, as I didn't when I created, you will find the next section absolutely hell for trying to find individual commands that you're going to be executing, as well as, you know, the actual place you're meant to perhaps go to and execute the next command, and so on and so forth. So just to give you an idea, by the way, of how much this can expand, so I've deliberately simplified this here. So the left-hand picture is, as I started off trying to directly read into from the cartridge or binary file, I guess you could say, into memory and then potentially operating on it with the CPU. On the right is what's happened subsequently, where I've had to split out the cartridge as its own individual file within a library file. And this has been actually simplified further down. There's a few more other files that have been generated as well that I've deliberately deleted and omitted just to show you. So I've added in 4 extra files here just simply for allocating extra memory, because depending on how much extra memory has been allocated in the cartridge, you may actually need to handle it in individual ways. And thankfully, it's actually well documented, I will say. There's also an implementation, by the way, if you're feeling very nervous at this point. You can find a pure Python Gameboy, or mostly pure Python Gameboy called PyBoy, which is well worth a look up as well if you're feeling very kind of concerned as to how you will implement something. PyBoy has almost certainly implemented it ahead of time for you, so you can use that as a reference point. But it does go to show you how much extra files this can balloon to when you want to start supporting stuff that doesn't fit fairly directly in memory. So this is, for example, when I started being able to play games like Zelda and Pokemon, this is the actual format I had at this point. So, and yes, by the way, that is a deliberate omission not to have MBC4. That is actually how it's listed in the Game Boy documentation, that it is meant to be in that order for some reason. I have no idea why. So it's not needed for Tetris, for example, but if you want to run those stuff, you will need it. So now moving on to CPU emulation. So provided you've actually read your file incorrectly, you need to get the individual instructions for what's meant to be executed, right? And I'm not going to go into those instructions in great detail because, frankly, I don't expect anyone here who knows assembly language, which is what most of these games were created in. But luckily enough, you don't actually need to know what it is really doing unless you're starting to build and develop your own games, because there's an entire doc that will essentially tell you this is the instruction you found at X, Y, Z position, and this is what you need. What this instruction will do. So we need to make sure, providing our file is correctly formatted, that we can actually retrieve a specific CPU instruction from that area, and then we need to parse it, and we need to execute it in some way. And I'll warn you in advance, by the way, when you're starting out, this is going to be the section you'll devote your most amount of your time to. PyBoy has an instruction set that's nearly 7,000 lines long in one file. So while each instruction doesn't fit on a single line, and indeed you don't need to implement every single one of them to get a lot of these working, there's kind of a tail off where most of the instructions fall within the first about 80% of your usage for about 20% of instructions, but you will need to implement the others as well as you go along. But still, it's nearly 7,000 lines, about 200 odd instructions, and more instructions potentially on top of that. You can simplify it down a bit, as we'll see, but there's still going to be a lot of coding here in it. And from the very beginning, it is worth trying to make sure to get this right, because a subtle bug here will take you forever to try and figure out. So I'm going to break my rule here and actually do a bit of introduction to what the CPU is like. So this is kind of an odd one. So there's 8-bit registers, which means that if you think of them, by the way, I was going to say like 8 bits. It helps if you think of a list that's 8 positions long, essentially, like you see at the bottom there where it says flags. That's what 8-bit means essentially in this case. So we have 8 8-bit ones called A, F, B, C, D, E, H, and L. And then we have 2 16-bit registers as well called SP and PC. And then just to mess with your mind even more, 2 of the 8-bit registers can actually be used as one. So you can use, say, A and F as AF. Just because, it likes to play it complicated. So just give an instruction as well, by the way. So PC, the program counter, actually tells the CPU where the next instruction in memory is. So it's literally, if we're going back to where we index directly into our list, it would be the position that we would need to go to next in that list. So for example, say we want to go to position 100, which is where our next instruction is going to be, and I'm going to actually show a few of these instructions, then PC would be set to 100, and then it would increment by 1 unless the instruction told it to be overwritten in some way. And also F is special, acting as what we call a flag register. So the last 4 bytes are written in this case, and then the first 4 are always going to be 0. So these indicate some sort of operation. You won't need to care too much about this when you're initially implementing it, but it is worth to implement as you go along. Simply because while a few simple games don't really use it, it does get used quite a bit in the test cases that we've discussed earlier on. So the DMG Asset 2, for example. Usually this is about indicating if you want something to stop, pause, or to carry some extra data or move somewhere else. So just give one example of one of the instructions. This is what we call a no-op or no operation. And the brightly colored thing you see on the left, by the way, is a small snippet from what we call the CPU opcodes of the Game Boy. You can find this just by Googling it. It's the first result up. And it's a fairly big document, to be about the size of an A4 sheet and then another A4 sheet underneath it, that lists out each individual code that you can expect to encounter at certain positions. So in this one here, for example, we have, this is almost in every single cartridge, but whether it's homebrew stuff, so like our test cases, or if it's a commercially available game. So once the Nintendo logo scrolls down, we're at this position 0, x0, 100, which is, I'm just going to say 100 from now on, just to keep it a bit simpler, right? So we always find this one, which is called a no operation, which literally means basically pass, which, increment the program counter by 1, go to the next memory location, and then execute whatever's there. So we can look this up by literally seeing what it says in this case. So if we go to that position, we'll find that it says 0, 0. If we directly go to our memory position, and Python, by the way, is a bit hit and miss as to whether it'll actually output this as a number or sometimes as a hex value. So in this case, we can go there literally saying 0, 100, or we could have gone saying 100 essentially, and it would register the same either way. So don't be terribly surprised if you need to spend a bit of time trying to understand this as well. But if we go to that location in any of our tests or any of the games, we should, it's not necessarily given, but we should find that it says 0, 0. So we use this to look it up. That's 0 on the left and 0 on top. That means we have our no op there with a 1 and a 4 and 4 little lines underneath. So what this means is essentially that the operation is called no-op, so you can map this to it later on if you want to. It's going to sometimes be a little easier to have, say, a dictionary of terms than do a redirect based on that. It affects 1 byte, which is why the 1 is there, because we're incrementing a count by 1. And then on 4 means that it takes 4 CPU cycles to execute this. So if you want to create a cycle-accurate CPU emulator, this is important. If you just want to get Tetris running, it won't necessarily matter a tremendous amount, but it is worth keeping in mind going forward. It can be very, very precise to implement some stuff and far less so for other items. And then the 4 items below indicate that there's no changes to be made to the flags that are already present from whatever step. So presuming we've executed either of the files we have so far, so the Nintendo boot logo, or if we use our DMG asset 2, this on the bottom left is what our initial sort of memory registers and whatnot should be set to. So program counter will be 0, 100, the A register will be 1, the F register will say 0, or it will say Z dash, it might be 0 depending on what way you've set your program to work, HC, and then B and C registers will be 0 and 13 respectively. So literally all that happens after this is that we just increase the program counter by 1, so it's now 101, everything else stays the same, and then we move on to our next position. So in this case, it's almost inevitably another instruction called jump, or JP. And again, when we go to that specific position, so 0, 100, or 101, sorry, we should find an instruction called C3 and some items after it. So initially looking at C and then 3, we find this one here saying JP A16. So the A16 means that it's actually 2 items of data that we need to take that will will sort of put together as if it was one 16-bit register rather than 2 8-bit registers. So in this case, it'll be 50 and 01. And just to mess with you a bit, by the way, the Game Boy is actually something we call little endian, which means that the smallest item, which is to the right, actually goes first. So this is not 50, 01. This is going to be 01, 50 when we parse it. So this will be 150. And as kind of with the no-op, nothing really necessarily happens. We just change the program counter to be this new address, which is 150. Everything else stays the same, and we then go to that new address. So, and this is a more complex one, then thankfully we're done with the CPU instructions being described here. So this is what we call an XOR A. So I presume people know what an exclusive OR essentially is, right? If not, you can look at it later on. It's a basic binary operation. So this says XOR A. So basically exclusive OR the value in the A register. And then just confusingly, just to mess with you, by the way, it actually means exclusive or what's in the A register with the A register, because we use the A register for these types of things to begin with. And this is something you won't discover unless you Google it, by the way. One of the annoying things you'll find during this is that Game Boy stuff is usually actually been documented. Someone has run into the issue you've had somewhere, but it's not in a structured manner. So you're not going to have, say, Stack Overflow. You're going to have a question on Reddit, for example. So do at least take some heart from that. Someone has probably had the same issue as you and documented it online. It's just, can you phrase it in a certain way that you will be able to hit it? Hence why I said we could probably use a course on how to build a Game Boy for direction. So in this case, we exclusive OR A with A, so it's 1 and 1, so that's 0. So the A register is now set to 0. Program counter increases by 1. And you'll notice underneath now it says Z 4 and 3 zeros. That means we set all the flag registers to this. So it's Z followed by 3 nothings essentially for that F register, and then everything else stays essentially the same. And this is one of those cases where you can simplify down the operation subsequently further. So, for example, XOR there takes A against whatever else is passed. So it could be XOR B would be A and B. XOR C would be C and B, C and A, so that sort of thing. So it can be useful to further narrow down the approach. So naive approach is probably that once you find all these wonderful CPU instructions that you start this right away. I'm going to tell you right now, don't do that. Because it is hell to try and find out when you've made a small mistake. And I guarantee you will, because if you're not used to this, it's inevitably you're going to make a mistake. Instead, use the file that you've actually been given. So at each individual step, do a printout or a dump of whatever that instruction is going to be, because most of these files are not actually that big, really, to be honest. Like I said, the Nintendo bootloader is literally 30-odd instructions, and some of those are actually data that's being passed as well. I can't remember how big the other one is as well, the DMG ASCII, but it's not tremendous. Most of these instructions get replicated pretty quickly once you've done that. So it's worth doing as well, because someone has also inevitably at some point said at some specific step what is the info meant to be at this case, and it's kind of straightforward enough in these early test cases as well that you can logically follow what should have actually happened by comparing the operation to what you currently have in memory and what's being dumped out. So it's very time consuming, but it is also probably the best case way you can do it, and then build a few tests from that for yourself just for convenience sake. Also as well, so these are only read-only files or ROM files. Definitely cut your teeth first on implementing only the read operations for this. So there are a few write operations that will be in the CPU as well. You won't encounter them for quite a while if you're using this test-driven approach. And definitely keep yourself to a read-only approach first, because it will simplify things you need to do far more. So I think I've actually accidentally given away my second slide, which is going to be literally what we should do. So implement a few instructions as you go along, each individual instruction, and then that will build up fairly quickly. In fact, you might be quite surprised. I think I implemented my first dozen instructions, got actually an entire file to execute. That's how much it is. And keep in mind as well that a CPU for each, think of it as essentially a for loop for each CPU cycle in this case. And then for each loop, we should really only be doing 3 steps per CPU loop, which is 1, fetch the instruction from the next area in memory, so wherever the program counter is currently pointed to. So maybe it'd be 101 for that jump case. Retrieve the data and the instruction from that location. So in the case of our XOR A, for example, retrieve, or maybe in the jump case, let's say, continuing that analogy, retrieve the C3 and then the 2 items of data after it, and then execute that instruction. And isolating them like this will make it much easier for you to find out if you've got a subtle bug somewhere, because you'll be able to do a print dump at some stage to try and find at each individual stage. Maybe your problem is being that you're not getting the value you actually expected at a certain location, in which case maybe you've not formatted it correctly, or perhaps it's just mapping to the wrong instruction set, but you won't know that until you actually check these individual steps, and breaking it down like that makes it much simpler. Also add maybe a CPU debug step as well that just simply prints out whatever the status is at a current step. You'll be thanking yourself later on for it. This is what we call kind of interrupts, and it's kind of a mixture of how we end up handling the graphics side and how we also handle user input. So if you're familiar with computer architecture, this might be familiar to you, but if not, basically what happens is every once in a while, depending on how it gets its input, the CPU will literally stop. It will stop executing, waiting for some sort of instructions. So in the Gameboy's case, this happens just shy of every 60 seconds. I think it's 59.7 times a second. If you're familiar with games, you might have heard stuff like 30 frames a second, 60 frames a second. This is kind of the same analogy, essentially. It's drawing the entire screen 59.7 times a second from the top left, scrolls over to the top right, and then it goes down a line, continues all the way down until it hits the bottom right, and then we'll go back to the top again, and that's 1 frame. And in that case, when that hits the very bottom right, having started at the top left, it triggers what we call an interrupt. So literally the CPU will stop, and it will trigger what we call a vertical blank. So at that point, there's a whole bunch of different things that can happen. It's literally could be waiting for user input. So this is when we actually take the user controls or input controls. So directional A and B if it's a start. Maybe we've included something as well to cancel the game or kill the session if you're on that. This is where you actually parse that. So you literally have a CPU wait instruction, and you wait for these flags to be raised at these addresses, essentially. And once again, I've said kind of already that once the CPU will take a lot of your time. This is the one that longer term is actually be far more of an irritant to you, because if you've got some sort of visual glitch on a game or an audio glitch, as the case may be, it can take a long time to try and figure out what exactly has gone wrong, because it's usually to do with timing, and it's almost inevitably at this sort of area is where you're actually going to encounter the problem for the first time is somewhere in here. It's certainly where most of the patches that are made over the long term end up going to. And as I said there, you can see the precise time there, 59.7 times a second. There's also a precise timing as well for if you want user input. Now, when we're emulating for Tetris, we don't necessarily care about these exact millisecond timings, by the way. You can ignore them to some extent, but do keep them in mind if you get odd visual glitches. And this is one example I encountered, by the way. So for graphics, we use Pygame for this. So if you want to brush up on some Pygame, this is actually how most emulators end up handling it. They use what's called the SDL2 library from C, and Pygame is just a nice Python wrapper around it for making games. But this is what happens when you don't do any testing whatsoever of what you're actually expecting. So I was flushed with enthusiasm, thinking, having implemented mappings to bringing up the actual pixels on the screen, thinking, oh great, I'll get the smiley face on the right. I actually ended up with the kind of weird, odd wise man, what it looks like at the bottom on the left there, like a wise man, some sort of temple from the looks of her, I don't know, the remnants of a face. And this is all just simply because the vertical timings are off. So thankfully you can fix these without too much difficulty. I think this was just a few minutes of work to get a few items fixed and a bit of Googling. But if you want to implement a lot of visual effects that are very nice and very sophisticated looking, it's usually going to end up being in here. You'll spend a lot of your time. So as I said, down to the millisecond in some cases, but a lot of the time it doesn't necessarily matter tremendously. It's just if you're going all the way and you want to play something very advanced. But most of these games, thankfully, don't really care too much about that. So as I said, for initial debugging, try working with the test files. So DMG Asset 2 was a good example there because it does use sort of a mixture of just about everything you'll encounter fairly frequently when you're actually using games. Ironically, the test files are actually usually more stringent about this than the games themselves, outside of maybe very specific sort of almost like cutscene-like moments where you see something very nice visually. Going to millisecond accurate isn't necessary for most games. Pygame is essentially, like as I said, a wrapper around a graphics library provided for C, and it also handles the audio aspect of it as well. Again, don't be too worried if you're confused about how this exactly works. You can take some lessons in Pygame. It's very well supported online. And as I said, there are other emulators out there as well that use either SDL2 or able to use Pygame. So there's a lot of examples you can find on GitHub for it. And also try doing things on the screen that are displayed constantly so that they can be updated, such as the score if you're in Tetris, for example, because those are in what we call a separate window that doesn't really get updated. It's not affected by this too much. So it's usually the first area that you'll actually draw that will come up regularly and be updated without any further issue. The final area will probably be the actual pixels or moving items themselves, so like individual characters in, say, Pokemon or in Super Mario, as the case may be. Also, I will say, and I'm just getting to thankfully the second to last slide now, we'll be using something called a visualizer. So this is something that's provided with, you can buy a copy of this if you want fuller support, or you can get it for free. So there's what we call a VRAM visualizer for something I think it's called a GB-ROM viewer that will show you as the pixels should appear for a certain area of memory. So this is what pixels should appear on the very opening screen of Pokemon before you've even pressed start or any button to continue. On the left. It looks very weird, but when you started actually parsing instructions correctly, it'll go and fetch the individual tiles, what do you call them, which is a collection of pixels, and it'll make far more sense than compared to what else you might be using as a comparison. Also, there is a debugger available with a Gameboy emulator called BGB, and this is very good if you're stuck at a specific point of view because you can do a dump of whatever's in memory at a certain point in time, as well as checking the timings and whatnot. So it's very good for doing a direct comparison to comparison when you're doing visual stuff. Okay, and so I'm going to wrap it up there. So I'm going to leave you with two final items. So one of them is writing an emulator, the first steps. This is written in Go, but is also very applicable to this because it covers what I've talked about in far more depth. And the top one is a whole test suite of ROMs. There are quite a lot of these. Most emulators will pass most of them, very good ones, but they will not pass probably all of them because it's a very exacting. Even the normal hardware itself that it's based on often will not pass all of these if you can dump them onto a cartridge. So it's a good test suite for rigor purposes, but don't be too concerned if you're starting out and everything is failing on these. Cut your teeth on something simpler first and then go to these. Okay, so thank you. You will be seeing this emulator again, by the way, in far more depth, hopefully, in Python meetups going forward. Perhaps I'm hoping to pitch a series of talks to talk about individual components of them in more depth.
Yeah, thanks. Very interesting. Yeah, just wondering, Python versus other languages to do similar. Do you have a sense of like specific challenges? Mm-hmm. And would you choose Python because you like Python, or because you think?
Python
best for this kind of thing?
Sorry, my keenness to answer, I was cutting you out there. So partially it was because I know Python the best. I knew it was possible because I had seen Pyboy, for example, and that's a very feature-complete version of a Game Boy emulator that has some bits that are written in C nonetheless, but that's just for performance reasons. So I wanted to prove that it could be done. But there are other emulators that are well written in other languages that I had considered. I had considered starting in Rust and even made a start in it because it seemed like quite an interesting new language to try, but I think it was just taking on too much at the same time, and I got very confused and decided to back off and stick with something that I liked, which was Python in this case, because it was relatively straightforward. It's not perhaps ideal. It handles a lot of memory stuff internally, so it can be a bit confusing sometimes as to what you're actually meant to be doing, and so there's a limited amount of stuff that you can compare to. So if I go to, say, a C-based emulator, it might be doing some sort of shifting of bits, for example, that you can't really do in Python, or at least not easily. So it can be difficult to understand perhaps what's going on, despite the fact Python is actually automatically sometimes doing that exact thing for you. So you lose some of the expressive power of having low-level operations, but it does abstract a lot of awkward stuff away from you. So it's a good first attempt if you want to learn computer architecture and get a basic game working. Beyond that, maybe something else might be a slightly better topic, but I'll continue with this as long as I can. Anyone else?
No, I think, okay.
There's someone over there, yeah. I'll be hanging around for a while afterwards as well if you feel too shy and you don't want to come up and ask about them, by the way, so don't worry.
Thanks for the talk. Game Boy emulation is one of the most popular programming topics. What I've heard is that the CPU is pretty quirky, and it's influenced by Zilog, but there's only a subset of instructions. Can you tell me about what kind of quirks and bugs that you had to work through to implement this?
It is, yeah. So it's kind of a mixture of two CPUs. I think they call it the Zilog Z80, which was used in a lot of computer and actually some home consoles as well in the 70s and 80s. And then it's kind of got some other custom instruction sets as well. So I think someone once referred to it as a truncated Z80. And it's kind of, it actually didn't really matter a huge amount to me because ironically, from my position of ignorance, I didn't know a full amount about the Z80 or any other CPU. I literally came in this intending to learn more about computer hardware and how that sort of worked because, as I said, it's kind of very well documented. It's just not very well put together in a structured format that you can follow it through end to end and have checkpoints along the way to mark your progress like you would in a course, for example. So ironically, it didn't really matter too much. I suppose the worst bit is, like you can implement about maybe 70% of the operations in Python without much difficulty, but then there's specific ones about dealing with certain types of addresses or certain types of writing to a specific section of memory that's very confusing. It's more, I would say, to be honest, what was more of a challenge was actually figuring out how sort of like addressing works and how hexadecimals and work and how, you know, you could retrieve specific instructions like that C3 I showed you for the jump operation, for example, how to retrieve that, how to get it back, how to debug was more of an issue, I think, rather than anything specific about the CPU. It's quite a straightforward CPU in a lot of ways.
Okay, thank you.
Okay, anyone else? I don't know how we're fixed for time, sorry.
Yeah, no, we're over time. Thank you. Thank you.
Okay, thank you.